So let's go into answer very similar questions for example, advection equations, right? So first of all, how do we approximate the derivative? Here we have advection equation plus a big U times du dx equal to 0. The only derivative we want to approximate is this one, because here the time derivative, as soon as we get rid of the spatial derivative, we have an ODE, and we can use an ODE solver, right? Like for the Euler or ODE 45. So to derive this, we use the same trick as we did before. We say, okay, partial u partial x is equal to an unknown a times u of I minus 1 plus an unknown b times ui plus an unknown c times ui plus 1. And then we do Taylor series analysis. We have a times ui minus delta x times the first derivative, and we have plus times the second order derivative, and we have minus times the third order derivative, etc. Right? And b is just multiplied by ui, c is going to be multiplied by ui plus delta x. This is just a very standard Taylor series analysis, and the plus delta x cubed divided by 3 factorial times the third order derivative. Okay, and we want this to be as close to du dx as possible. So we want the first term to cancel to 0, which gives us a plus b plus c has to be equal to 0. We want the second term to not cancel but gives us du dx, right? So we want the second term to add up to 1, which means minus a times delta x plus c times delta x should be equal to 1. Okay, we want the third term to cancel. So we have as little error as possible, which gives us a times half of delta x squared plus c times half of delta x squared should be equal to 0. And that's all the equations we can satisfy using 3 numbers a, b, and c, right? Okay, so so the third equation, for example, just a plus c is equal to 0. So a is equal to minus c. And substitute that into the second equation, we basically get that a has to be equal to minus 1 over 2 delta x, right? And c is equal to 1 over 2 delta x. Basically, this is from the third equation saying that a is equal to minus c, and put that into the second equation. So with that, if you now look at the first equation, b has to be equal to 0 for the summation of everything to be 0. So this leads us to approximation of partial u partial x is equal to ui plus 1 minus ui minus 1 divided by 2 delta x. And you can derive any finite difference scheme that way. All right. So this is known as the central difference. For the first derivative, and let's plug it into the differential equation. What we get is dui dt plus a big U times ui plus 1 minus ui minus 1 divided by 2 delta x is equal to 0. Right, so again we get a set of ODEs. Okay, right, so how much error is that introduced? So okay, so we have answered the first question, how to approximate a derivative with arithmetic, right? So we derived this central difference operator. The second question is, how much error does this approximation cause? Okay, so then what we do is we substitute the a, b, and c we derived from canceling as many terms as possible and see what is the first term that is not cancelled. Now the first term that is not cancelled is here, right? Because we have a is equal to something minus, c is equal to something positive. So these two cannot add up to something something 0. And once we do that substitution into here, what we get is this is equal to, okay, the derivative we want to approximate, which is from here, and this term is 0. We get plus the delta x cancels with this delta x cubed to get me delta x square, and we have a half here, so it's going to be also over 6 times the third derivative of u. So this is going to be the leading error term in this central difference approximation. So now with that approximation, what is the order of accuracy of the scheme? Second order, because yes, the error term scales with delta x squared, right? Although if we don't know the true solution, we don't know what is the third derivative, therefore we don't know what is the exact error added every time step. But we know the error scales. We know the error decreases by 100, by a factor of 100 if we decrease delta x by a factor of 10. So that's the effect of a second order scheme.